Hello everyone, and thank you for joining this session. I appreciate your time and interest. My name is Hanife Akça and I'm currently working at Department of the Soil Science and Plant Nutrition at Ankara University. Today I will be presenting the result of my recent study on effect of nanocalcium on broad bean, plant growth and calcium uptake in soil and soilless conditions. Okay, let's start. As you know, calcium is a key nutrient for plants. It helps build strong cell walls and membranes. It also regulates growth and development, especially in young tissues. With a growing population and shrinking arable land, boosting crop yields by 2050 is essential. To meet this challenge, we need more efficient farming practices and must also address poverty and hunger. Chemical fertilizers still play a key role in ensuring global food security. Overshare of chemical fertilizer is now a major global issue, both economically and environmentally. Nanofertilizers offer a promising alternative. Thanks to their small size and special properties, they can release nutrients slowly and more efficiently, reducing losses and improving plant uptake. In this study, I applied both conventional calcium oxide and nanosite calcium oxide nanoparticles to broad bean plants. The treatment were carried out under both soil and soilless conditions and applied in two ways, through the growing medium and as a foliar sprays. This allowed me to compare the effectiveness of nano and conventional forms of calcium under different conditions and application methods. Let's look at materials and methods section. In this slide, you can see the synthesis producer for the nanocalcium oxide material. First, I started by preparing 0.5 molar calcium nitrite solution and added 0.7 molar sodium hydroxide dropwise using a separating funnel. The resultant mixture was processed in a microwave oven at 800 watts for 10 minutes, then cooled to room temperature. After precipitation, the product was washed several times with distilled water and dried at 80 centigrades. To verify the composition of the synthesized material, I conducted X-ray analysis. As expected, calcium was the dominant element, making up over 49% for the total content. The low presence of the other elements like potassium, phosphorus, and magnesium suggest that the final material was relatively pure and suitable for use plant experiment. Minor amounts of silicon and aluminum were also detected, which may have come from synthesis residues. Here I also show the TEM image of the synthesized nanocalcium oxide. The particles appear well disappeared and form loose aggregates with individual size well below 100 nanometers. The small particle size and high surface area are critical features that enable the slow and controlled release of the calcium when applied to plants, making this material an effective nanofertilizer. In this part of the study, I grew broad bean plants in a hydroponic system using Hoagland solution. I tested two forms of calcium, regular calcium oxide and nanocalcium oxide. These were added the nutrient solution and also sprayed on the leaves. The system was aerated every 30 minutes and the solution was refreshed weekly. I started the application in mid-April and I harvested plants on April 26. The control group received only the calciums already in the Hoagland solution. Here you can see photos from the greenhouse setup phase of the experiment. Broad bean seedlings were placed into the hydroponic system and treatments were applied as planned. The system was monitored regularly to ensure stable growing conditions throughout the trial period. You can see here the soil experiment setup and treatment groups. The main objective was to evaluate the effect of calcium oxide and nanocalcium oxide on calcium uptake and translocation in broad bean plants. The treatments included 2 different soil doses for both calcium oxide and nanoparticles calcium oxide, 50 and 100 ppm, as well as separate foliar applications. In total, I had 7 treatments, a control group, 2 calcium oxide nanoparticle soil doses, 2 calcium oxide soil doses, and the foliar application for each form. This design allowed me to compare both the doses affect the application method. After harvesting, I separated the plant materials into different parts: roots, old leaves, young leaves, depending on the trial type. I first recorded their fresh weight and dried all parts at 65 centigrades until constant weight, and measured their dry weights as well. The dried samples were finely ground and digested with nitric acid using a microwave digestion system. Calcium concentrations were then measured using ICP-OES. This allowed me to determine the total calcium content in the different plant organs and evaluate how calcium oxide and nanocalcium oxide affected calcium transport in both hydroponic and soil-grown plants. Figure 1a shows the fresh weights of old leaves, young leaves, and bean under different calcium oxide and calcium oxide nanoparticle treatments in the soil conditions. The calcium oxide nanoparticles 1 doses from soil, and calcium oxide nanoparticles 2 doses, second doses from soil treatments significantly increased the fresh weight of the old and the young leaves compared to the control. Calcium oxide nanoparticles first doses from soil had the highest value for the old leaves. Foliar treatments resulted in relatively lower fresh weights. Soil applied nanocalcium oxide, especially first doses, positively affect leaves biomass more than conventional calcium oxide or foliar applications. Figure 1b presents the dry weights of all leaves, young leaves, and bean. Differences are less important compared to fresh weights. Calcium oxide nanoparticles second doses from soil and calcium oxide first doses from soil slightly increased dry weights of old leaves. For young leaves and beans, many treatments show not significant, indicating no statistical difference from the control. While some trends are visible, most treatments did not significantly affect dry weights. Figure 1c shows the total calcium content in old leaves, young leaves, and bean. Calcium oxide nanoparticles second doses from soil treatment result in the highest calcium concentration in both and young leaves. Calcium oxide nanoparticles first doses from soil also increased calcium uptake compared to the control. Foliar calcium oxide nanoparticles and calcium oxide showed moderate increases but were generally lower than soil applied nanocalcium oxide. Calcium beans remained low in the treatment. Soil applied in nanocalcium oxide was the most effective at enhancing calcium uptake and translocation, particularly in leaves. Foliar applications were less effective in increasing calcium content in plant tissues. Overall, soil application of nanocalcium oxide significantly improved both BMS and calcium uptake in the broad bean plants, especially in old and young leaves. Among the treatments, calcium oxide nanoparticles second dose from soil showed the best performance in the increasing calcium concentration. Foliar application had a limited effect compared to the soil application. In figure 2a, calcium oxide nanoparticles treatment result in significantly higher fresh weights in all plants parts compared to calcium oxide, especially in old leaves. Calcium oxide nanoparticles showed the highest fresh weight, statistically distinct from the calcium oxide and control. Root and young leaf weights were also higher with calcium oxide nanoparticles, though the differences were smaller. In figure 2b, calcium oxide nanoparticles significantly increased dry weight of old leaves, followed by the calcium oxide. In roots and young leaves, differences were less important, but calcium oxide nanoparticles still perform slightly better. In figure 2c here, old leaves had a highest calcium concentration under both treatments, with no significant difference between calcium oxide nanoparticles and calcium oxide. In roots and young leaves, calcium concentration were similar across treatment and significantly lower than in old leaves. Overall, under hydroponic conditions, nanocalcium oxide improved both biomass and dry matter production, particularly in old leaves, while calcium accumulation was highest in the old leaves. For both treatments, calcium oxide nanoparticles was more effective in promoting overall the growth. In figure 3a, foliar treatment showed the highest fresh weight in old leaves, significantly higher than calcium oxide nanoparticles. In root and young leaves, both treatments had a lower values with no significant advantage of calcium oxide nanoparticles. In figure 3b, similar to fresh weight, calcium oxide led to the highest dry weight in old leaves. In roots and young leaves, differences were minor and overall biomass remained low compared to the soil application result. In figure 3c, both calcium oxide and calcium nanoparticles increased the calcium concentration in roots and old leaves, with no significant difference between the two. Calcium in young leaves was lower and showed only slight differences between treatments. Under hydroponic conditions, foliar application of calcium oxide and calcium oxide nanoparticles had a limited impact on biomass production. However, but both treatments increased calcium content in roots and old leaves. Calcium oxide was slightly more effective in enhancing growth, especially in older tissues. To summarize the entire study, I evaluated the effects of both conventional calcium oxide and nano-sized calcium oxide on broad bean plants under soil and hydroponic conditions. The result clearly showed that nanocalcium oxide was more effective than calcium oxide, particularly when applied through the root zone. In the soil experiment, calcium oxide nanoparticles significantly enhanced plant biomass and calcium uptake, especially in older leaves. Soil application was consistently more effective than foliar spraying. In the hydroponic system, calcium oxide nanoparticles applied to the nutrient solution led to better growth and dry matter accumulation than calcium oxide. Foliar applications in both systems had limited effect on calcium translocation and biomass increase. Calcium mainly accumulated in old tissues with lower levels in young leaves and pods. This suggests that calcium mobility remains limited, but root zone nanocalcium oxide applications can enhance the availability. Overall, nanocalcium oxide is a promising tool for improving calcium nutrition, and it may contribute to more efficient and sustainable fertilizer strategies in agriculture. I would like to thank all of you for your interest, attention, and participation throughout the presentation. Thank you very much.